Hello everyone and welcome back to the Victoria Game Engine series. This is episode 13 and today we're going to be starting on our string library. So as you may be familiar with other things earlier on in the series such as vectors and arrays and variants, we want to be creating our own custom data type. So we're not going to be using the std string for a lot of our projects because we want to make sure that we're managing it by ourselves because we get a certain more degree of freedom over using these standard implementations. What this means, however, is that we are going to have to write a fair bit of code to get all of this to work, and that's all going to be going under core because it's going to be a very fundamental type for the rest of our engine to use. So with all that said and done, let's go over to here under core, create a new folder. We're going to call it string because this is where we're going to house all of our different string operations. And we're going to create a file called vstring.h. And this is where we're going to contain all of our string functions. As with every other file, we're going to start out with a pragma once up at the top. And then we're going to want to include our type defs as well. So we know that we have all of the basic information we need. And under here, we're also going to go and include from core data vector.h. This is because the vector type is our managed array of cars, and therefore it means that some of the functions we will be creating are vastly simplified when using the vector type over managing a pointer ourselves. So under here, we're going to go and write a class string. It's not going to extend from anything because it's going to be, again, a very basic type. And it's going to have a couple of things. The first thing it's going to have is going to have a private field, and this is going to be a vector of cars called data. And this pointer is going to be all of the characters in the string that is currently being used. So this is the only private piece of information that we're actually ever going to need to know. It will just be the vector itself because that's all it needs to manage the data. And under here, we're going to contain a couple other things. First up is all of the basic functions that already exist in the vector type, but we need to extend them for the string type because vector is a private field. So under here, it's going to be force inline. We're going to get car pointer ptrw. Again, just like the underscore data type, we want to make sure that we can get access to a writable pointer for the data. So within here, we're just going to return data.ptrw. And that way it returns a non-constant version of the character array. Then we're going to want the same thing for a const car pointer, and it's going to return data.pointer. Again, these two functions act very similarly, aside from the fact that the .ptr version returns a constant, non-modifiable version, whereas the pointer with writing permissions returns a modifiable version instead. While it seems like functions like these really probably shouldn't be accessible to the string, they are actually needed for some operations and some high-level manipulation within the rest of the engine, so we keep them public here. Next up is force inline error resize. And we're going to pass int p size. And this is going to return data resize, passing the p size through as its argument. Nothing really to comment about there, just allows us to trim the number of characters that exist in an array if need be. Then we're going to have a whole bunch of miscellaneous functions. So we're going to have force inline car get int p index. And this is going to return the character at the current index. We're going to have a similar thing for force inline void set. Again, getter and setter functions, these will effectively act the same as using our index operators, which we'll get onto in a moment. But these are there for those who prefer to use getters and setters manually. We're also going to get a helper function, force inline int size. And this will just return the size of the data. Another thing to note about this type specifically is that because C strings always ends with a null terminator, so rather than tracking the number of characters in the string, it just returns a null terminator to say when the string has ended. This means that the size of the array is not actually going to be equal to the number of characters in it. It's going to be the number of characters in the array plus the null terminator. So whenever we're doing allocations or changing the size of the string manually through code, we're always going to have to keep that in mind. That being said, there will be a function a little bit further down that kind of gets rid of this problem for us if need be. But there are a couple other functions. So we have force inline void clear. And then this just calls to data.clear to get rid of all of the characters in the array. We also call to force inline bool is empty. And this returns if length, which is a function we're about to write, is equivalent to 0. You may wonder why we're using the own classes type here, if it just means that you can write this code and it acts the same. And this is just so that the option exists for either way to be used, depending on the programmer's intentions. And as I mentioned earlier, we also have our operators. So we have force inline, car, and operator brackets, int p index. And this just returns the data at the given index. And we also have the same thing for const car operator int p index const returns data p index. And again, all these will do is return a non-const version of the character within the string. If you access the string like string s3, for instance, that will just return the character at the given index. And because of the way C++ works, we're going to need a non-const version of it and a const version of it, depending on what kind of function we're writing. Below this, we have our length operator, so force inline int length const. And this will just query the size of the string and then return the string. If the size of the string is not 0, it will return 1 less than the size. Remember about the null terminator. And otherwise, it will just return 0 because the string is empty. And these are all of the inline operators that we'll be having set up. But there are a few other functions that we'll want to find. So next up, we're going to want to look at a const car get data const. What this does is, as you can imagine, by the fact it returns a const car, it just returns the C string version of the function. And to save myself doing a whole bunch of writing out, I'm also going to go and copy and paste a couple of operators that we'll be writing in the source file. And these are as follows. So the operator equals here is simply assignment operators. These take a string on the right-hand side and assign it to the left-hand side. There are also equivalence operators. So we do the same thing for if two string types are equal, if two C strings are equal, and if individual characters are equal as well. And we do the opposite versions for the not equal operators. We also have some appending operators here. So for when we want to, instead of, so when we want to create a string out of multiple smaller strings within code, we can also do these. And before we write our constructors and destructors and some other miscellaneous functions, we are also going to add an operator const car. And this will just return get data. What it does is grabs the string as a C string to allow for slightly easier implicit conversions. And then we're going to have a assignment constructor. So const string and p from. We're also going to have string const car p from. And this is going to call to copy from p from. And we're also going to have an empty string constructor, which will do nothing. This is also reminding me there is one function that I believe I'm missing, and that is below here. Like P shouldn't be there. We're going to have a protected field. We're going to have a void copy from const car p string. I'm going to have a void copy from unchecked const car p string const int p length. Again, these two functions are very similar to the ones that you'll find in Godot. And then below this, we are going to have a couple other functions. So we're going to have a string operator plus const p left-hand side const string p right-hand side. This will exist as a way to concatenate two strings. And then we're going to have a string v format from a const car p string ... And this we'll get onto in a moment. Now, with all of these functions written out, we can now go into our folder, create a vstring.c++. And within here, we're going to be writing the source definitions for all of these functions. All right, so in terms of includes, it's going to be relatively simple. The first thing we're going to want is, of course, we're going to want the header file. So we're going to call vstring.h. Then we're going to want to get a couple of things from the standard library. So those are include stdio.h, include stdarg.h, include string.h, and include math.h. The last one we may not use today, but it is necessary for some functions that we may want to write later on, so we'll leave them here for now. First function up is the getData function, and I'll simply paste it in as is. So this function is relatively simple. All it needs to do is it checks first off if there's anything within the array. So if we have attempted to append anything or clear anything at any point, there should be data within the array, and therefore we need to return that data. Otherwise, if there isn't anything, if the size of the array is 0, then we just return a blank string here that still gets accepted as a valid empty pointer because it's an array of a null terminator, and that will get returned properly. Generally speaking, that is very unlikely to happen. Most of the time, a null terminator will appear, so it will just return a null terminator from here anyway. But for the most part, this is how the function is working. Next up is our two assignment operators, and they are as follows. Since we can compare if the two are the same, if they are the same, then there's no point copying, so we just double check that if they are equivalent. Otherwise, we just assign the data over from one to the other. Since the vector already has an equals assignment operator, it can do that as it will. I will note now there are a lot of problems currently with our vector implementation, specifically with the sharing of the same pointer. So to give an example here, whenever we try to, so sometimes when we call to ref and we want to unref our current piece of data, the data that it's using, aka the pointer essentially, still has memory elsewhere. And what that means is that the pointer is still being used in multiple instances. And therefore, when we try to go and free it, sometimes we'll end up with what we call a double free. And that will try to free already freed memory or a null pointer. And that's an invalid operation. And we'll get a error thrown up depending on what version you're using. So you'll get a segmentation fault generally on Linux, and we'll get a allocation thing thrown up by the Windows standard library when we're using Windows. This is a problem that we'll get back to when we have created, when we've created atomic counters and created a way to prevent this problem from happening, but this is something that you will have to keep in mind when using the string function, as it is very finicky at the moment and this specific issue is something that we should come back to fairly soon into the series. Maybe next episode, maybe a little bit further after, because there are a couple other foundation points that we do need to build first. So here we'll paste in all of our equivalence operators. I don't know why that's there. That's very weird. I didn't know that was in the source code. Again, all they'll do is they'll just compare that the actual vector itself is equivalent and compare it to the other one. Realistically, this is not something we should be doing, especially not here. I'll give a very basic reason why we shouldn't be doing it here. Since it is very expensive to do such an allocation, so creating a string and copying it in, that allocates some memory for the comparison. We really shouldn't be doing this, and I'll probably end up fixing that at some point, because a lot of the code here really could do with being a little less expensive to calculate, and otherwise we'll move on. And the not equal operators can probably be made to be the inverses of these, rather than being just the not of the equivalence. So we may fix that in a future video. For the sake of keeping this one fairly brief, we'll move on from that. Next up, we have our string appending operator. So what this does is it looks at the string on the right-hand side and effectively takes the current string and adds it to the other side. For some reason, I didn't have an underscore there. That's kind of weird. Anyway, from here, you can see that if the length is 0, then we want to set this to be the other operator and return that, because there's nothing in this string. We just want to append from the right. And otherwise, we need to query for the length. Then we look at the other side's length, and if that's also equal to 0, then we return this string, because otherwise there's nothing that we need to append. Otherwise, we get the length. Then we get the pointer for the right-hand side, because we want to start copying data in from that. We then resize the current data array, so we have all of this stuff for our current string, plus the other side of the string, plus a null terminator, and we get our current pointer from that. And then we run this operation here, which will just run for every item within our string. And we'll look at if I is less than the left-hand side, then we want to copy data in from our left-hand side pointer. Otherwise, we copy the data in from the other side. And then once both of those operations have occurred, we then set the last item in the array to be the null terminator and return the current string. There's a couple others like this, so I'll just put them in here as follows. They follow a very similar design pattern. So here, when we're adding an individual character, we query the length. If there isn't a pointer, then we just resize it to be 1 byte wide. And we do some extra stuff with appending the character. And it's effectively the very same as with the copying in. Then we have the plus operator. So this will look at the current string, look to the string on the right-hand side, and add those two together. As you can see here, it basically does the same there and returns the value for that. And we also have our non-class specific operator here. The reason we need this sort of global operator that isn't specific to the class is because the operator can't be called if it's part of the class and you have two strings, and the string on the left-hand side is a C string, because C strings obviously need to be converted into strings so that we can do the operation. But with this setup, it allows us to have that happen as well. Next up, we have our class constructor. Again, very simple. All it does is references the data from the other string. Beyond this, we have our copy from function. So again, what this does is it takes a C string, looks at the string it's trying to copy from, checks things like the string's length. That's why we need the standard library includes. And if the length is 0, then we resize it to 0 and return. Otherwise, we resize it to the extra length. Do some more pointer manipulation. Copy the data in, and otherwise everything is as is. We also do something here that just to make sure that in the case that there is a null terminator in the middle of the string, for whatever reason, but we don't want the string to end at that point, then we add a space, and otherwise we copy the characters in as you would expect. Now there's a very similar string here, and that is copy from unchecked. The difference between copy from and copy from unchecked is that copy from unchecked makes a couple of assumptions. It first off assumes that the string that we're dealing with isn't a null pointer, it's an actual string that you can read from. It's also got a length that's greater than just being a null terminator, so it has several characters in it. And from that, it greatly simplifies whatever the copy from operation is. So if our functions are using the copy, are already determining these things, then we can go ahead and use copy from unchecked because we don't need to worry about any of that information in the first place. And last but not least, we have our vformat function. This is a variadic function. So it looks at, it can have the first string, which will normally have a bunch of identifiers in it, and will then use those identifiers to format the string in a certain way. So we'll have it here. And it's a very useful function to have because a lot of what it does just allows us to construct new strings that can then be used in places where we would normally not be able to use a string because it needs, it needs to be formatted in a certain way that applies to that format, and we don't have that format existing in our vstring library at the moment. So what it does is it creates a really massive C string. So it creates a 32,000 character long character array, zeroes it out, then gets a VA list, starts that VA list, formats everything into the buffer, ends the VA list. Then we grab the size of the actual string that we're now dealing with, which we look at from the C string. Then we resize the string to be the current size plus 2, because remember, we need to make sure that every character in the string is formatted in plus the current null terminator. That's what this does. I'm also going to change some of the stuff here so that the formatting is a little bit nicer. And then we set the last character to be 0, and then we return the string that we've created. And all in all, that is pretty much all of the functions we are going to be dealing with in our very early implementation of this string library. Now that we actually have a string class, we can start using it in parts of our code to create some stuff that we previously weren't using. So for instance, in our display manager, we want to go and change this const char here to use a string instead. So we're going to go up here, we're going to include, when you spell it right, core string vstring.h, and instead of using const char here, we are going to use const string and pname. Now that's going to need some changes in both of our display managers here, so we're going to go and do that right now. So here in display manager windows, we are also going to change this to be a const string, and we're going to have to make the same change in the source file as well, like so. Likewise, we're going to do the same change in our display manager x11 because that is going to cause problems, and I don't want to have to update this for Linux at a later point because we really should take care of it now. And for the meantime, that's pretty much everywhere we're going to be using them. However, it should be noted that from here on out, we are going to do our absolute hardest to make sure that we are using our string library over using the other implementations, so just general const chars, because it will give us a lot more management of strings, better comparisons, so on and so forth, that isn't normally offered within standard C++. At least not without using the libraries. All right, well, if you clean the binaries first, and then go and hit Control-Shift-B, we should see that it compiles properly. Everything's done. We can now hit F5, and you should see nothing has changed about the engine, but we are now using the strings internally, and that makes our lives a little bit easier. So we can go and close that window. And that's pretty much everything for this video. Thank you very much for watching this video. This was kind of a sort of intermediate step that we're going to have to do, and there's going to be a couple more of these that follow, where the video that we're working on, the content that we're doing within that video needs to be done so that the setup for later videos and later progress on our renderer can be done in adequate time. So for instance, the next video we're going to be doing in the series is probably going to be talking about smart pointers and references and our base kind of object type that we're going to be using, which if you know Godot, you'll be very familiar with that system, and that is something we're going to start implementing next episode. And once we've done several implementations of that, we can actually start moving on to other things, such as doing a file system so that we can start having our shaders in unique files and generally move away from the current format that we have into something that's slightly more robust. And eventually, once all of that's done, we'll have a very strong base to start leaping into some of the abstraction of our shader code, which once that's done, we can start moving a lot of this into a separate rendering server or rendering manager that then does all of the OpenGL work for us and keeps most of the OpenGL stuff under the hood so that we don't have to worry necessarily about dealing directly with OpenGL code when we're creating our games. Once again, thank you very much for watching, and I'll see you in the next video. Goodbye.